Hi, today I'm going to be presenting homework question number 29 on section 8.2 of the textbook. And the question is to find all solutions of the recurrence relation of an equals 2an minus 1 plus 3n. And so the first thing we gotta do is basically figure out the formula, which is an equals an of p, and an of p is a particular solution for the non-homogeneous linear recurrence relation, and adding it to anh, which is the solution for the linear homogeneous recurrent solution. So the first thing I did was solve anh, which is basically an equals 2an minus 1. So we're basically solving this, and we're ignoring this because this isn't homogeneous. So we get anh equals 2an minus 1. And then what I did was I converted all this to r to the power of n. So it would be r to the power of n equals 2. Instead of a, it would be r to the power of n minus 1. And divide both by r to the power of n minus 1 on both sides. And you get r to the first power equals 2 because this canceled out. Subtract 2 on both sides, and you get r minus 2 equals 0. And you'll be left with this, which is the root for the characteristic equation. And what you do with that root is you basically come out with this, which is a1 and 2 to the power of n. Now the reason it's 2 because you're plugging in the root inside here, and where a1 is a constant coefficient. So now we solved the an of h, the homogeneous. Now, and then what I did next was I solved the non-homogeneous recurrence relation. Which is this number right here. So because f of n is 3 to the power of n, the formula would be ANP would be equals c times 3 to the power of n, where c is a constant coefficient. And then what I did was ANP equals 2an plus 3n, 3 to the power of n. So I basically just want to remind myself that I'm focusing on this equation. I put it back here, and I switched it with ANP, and because ANP equals c times 3n, that's why I switched it with c times 3 to the power of n, equals 2c times 3 to the power of n minus 1 plus 3n. And so basically I'm plugging in this with this, so that's why it's 3 to the power of n minus 1 plus 3 to the power of n. And then I factored it out, so dividing it by 3 to the power of n minus 1, which comes out with c times 3 to the power of 1 equals 2c times 3 plus 3 to the power of 1. And then when simplifying it, I got 3c equals 6c plus 3. Subtract 6c on both sides, and then I get this, divide negative 3 on both sides, and c equals negative 1. So I go back to the so basically I plug in this c to the non-homogeneous formula. So ANP equals -1 times 3 to the power of n, and ANP equals -3 to the power of n. Now, since I have ANP and I have ANH, I have both ANH and ANP, I can finally solve the non-homogeneous question. So AN equals -3n plus A12 to the power of n, and that's the solution to the non-homogeneous linear recurrence relation with constant coefficient. And the next question was to find the recurrence relation in this part with the initial condition A1 equals 5. So I brought back the original recurrence relation. This is n equals 1 because of A1. So A1 equals -3, and then I plug in 1 for all the n's. A1 equals 5, so that's why there's a 5 there. -3 plus 2A1, add 3 on both sides. 8 equals 2A1, divide 2, and then 4 equals A1. And then since I found A1, I can plug this in here. So it would be AN equals -3 to the power of n plus A1 2. So then this would be AN equals -3 to the power of n plus 4 because we found A1 times 2 to the power of n. And simplifying this would be AN equals -3 to the power of n plus 8 to the power of n. And that's the solution with initial condition A1 equals 5.